Okay, so in this lesson we're going to take a look at the question of independence between events. And it's a really important idea. It's an extremely important idea in probability, and one that often gets confused, especially confused with mutually exclusive. So we're going to try to lay down some good groundwork here and make sure that we discuss some good formulas for independence. So a random deck of 52 cards is shuffled and 2 cards are drawn. What's the probability that both cards are diamonds if the cards are replaced after being drawn and the deck is reshuffled? So first of all, with regards to independence, independence is, or two events are considered independent if an event does not affect the probability of some second event occurring. And usually this question of independence comes into play when we are determining the probability of two events happening. So the two events that are happening in this question are the first card being a diamond and the second card being a diamond. And we'd like to determine if these two events affect each other. If they do not affect each other, then they are independent events. However, if they do affect each other, they are considered dependent events. Well, the way in which the cards are drawn can determine whether or not they are independent. For example, if the cards are replaced after being drawn and the deck is reshuffled, then the probability that the first card is a diamond would equal 13 out of 52, because there are 52 cards in the deck and 13 of which are diamonds. Now, if that card is then replaced in the deck is reshuffled, the probability that the second card is a diamond would still equal 13 out of 52. Now, we could write that as the probability that the second card is a diamond given, and that's what that vertical line stands for, the first card is a diamond, and the probability would still be 13 out of 52 because the first card was replaced in the deck and the entire deck was reshuffled. So now I know the probability that the first card is a diamond. I also know the probability that the second card is a diamond. I would multiply them together to find out the probability that the first and the second card are diamonds. And that total probability would equal 13 out of 52 squared, or 1/4 squared, or 1/16. Now, what if we did not put that first card back? So in this case, the probability that the first card is a diamond is still 13 out of 52. Now, if I'm not replacing that card, there are now only 51 cards left in my deck, and only 12 of which are diamonds. So the probability that the second card is a diamond, given that the first card is a diamond, would now no longer equal 13 out of 52, it would equal 12 out of 51. And the reason that changed from the previous problem is because in this case I am not replacing the card. So in this case, the probability that the second card is a diamond has been affected by the first card being a diamond. These two events, in the second case with the cards not being replaced, are considered dependent events. Whereas in the first problem, the two events were considered independent. The first event did not in any way affect the probability of the second event occurring. So if I wanted to know the probability that the first and the second card were both diamonds without replacement, 13 out of 52 times 12 out of 51, which would equal 1/4, times 12 out of 51, ends up equaling 3 out of 51, which is 1/17. So the probability that the two cards are both diamonds without replacement is 1/17. So a couple of formulas that we just really used here. The first is the probability of A and B. Well, the probability of A and B is equal to, theoretically, the probability of A multiplied by the probability of B given A. This is called a conditional probability. Now really, this is the only AND equation that you need. This P of A times P of B given A. And the reason that is because if A does not affect B, then we can say the probability of B given A is equal to the probability of B. Thus, the probability of A and B is equal to the probability of A times the probability of B. And by the way, this piece over here is my proof of independence. In other words, if I can show that the probability of B given A is equal to the probability of B, then I know mathematically, formulaically, that A and B must be independent events. So I hope that answers the question regarding independence.